All right, now we're going to do the last part, the second and last part of section 6.2, which deals with transforming and combining random variables. And I want to look at a few tougher problems. I didn't include this in the last video because it tends to be a bit confusing. The main emphasis of section 6.2 is what we talked about last time, and that's really the main thing to understand. And I don't want kind of the potential confusing nature of these problems to distract you from the main issues going on earlier in the chapter, which are dominant themes. But these are problems that have occurred and they can occur. They haven't occurred that much, but they certainly can occur on the AP Stats exam. And it deals with subtracting random variables. And going back to our little formula, you may recall, is when you have random variables and you're combining them, when you subtract them, you're going to subtract their means. And I think that's that makes sense, okay? But when you subtract, now if the two variables are independent, when you subtract two random variables, you cannot subtract their variances, you add them. Because you're basically combining the variabilities of the two distributions. And so that's something that students can have a difficult time remembering, but it's something that in essence you need to know. And you say, well, when is that going to come up? Well, so you recall the last problem that we did in our last video. We have Anita, and she makes money by selling cakes and pies, and the amount of money that she makes from cakes follows a approximate normal distribution with a mean of 400, standard deviation of 70. The amount that she makes from pies follows an approximate normal distribution with a mean of 500, standard deviation of 60. All right, and so we talked about, well, what's the total with cakes plus pies, which you would just add the two means. It'd be 400 plus 500 is 900, but you add their variances. You have to square the standard deviations and add them to get the total variance, and then take the square root of that to get the standard deviation. But what happens when you ask something like this? All right, it says, if you were to randomly select a week, what is the probability that Anita makes more money from pies than cakes? And there's a couple of different ways to do this. So you're, in essence, comparing two distributions. So what's happening here is this. If we think about what's happening with these distributions, so when we've got the cake distribution, let's say, and so it's centered around 400, okay, and it's approximate. So here's the cake, and so it's centered around that. So it averages 400, but different weeks she gets different amounts of money from it, sometimes like 450, 500, or whatever. All right, but then somewhere up here, 500, and here's the amount of money she makes from pies. In general, she makes more from pies. She makes about 500, okay? So most of the time, so that's not the prettiest normal curve in the world, but anyway, in general, this curve's more than this one. And that's what's going to happen on most weeks. But it could happen by chance that you get this amount of money from pies in a week. And it could happen by chance that you get this amount of money from cakes. And cakes is more than pies. Most of the time, that's not going to happen. But it can happen. It does happen some of the time. So this is pies, okay? So the question is, if you were to randomly select a value from this curve and randomly select a value in this curve, what's the probability that she's going to make more from pies than she is from cakes? Now, you're expecting that to happen most of the time, but like we said, not every time. So when you're comparing two distributions, you want to subtract them. And so what I'm going to do is I'm going to say, well, let's look at pies minus cakes. So we'll look at a new distribution, pies minus cakes. In other words, if you were to just a large number of times take a random value from this and a random value from this and subtract them, and do that again and again and again and plot those points. Guess how it would vary? It would vary approximately normally, which we're not going to get into that proof at all. But in regards to the means, what does this mean of pies minus cakes? Well, that's sort of intuitive. You just subtract the means. That would be 500 minus 400, which is 100. So that would be the average difference, and here's where it's a little counterintuitive. You would think you would subtract the variances, but you don't. You still add them. So even when so the variance of P minus C, the variance of P minus C is you still add those. And so it's still going to be 8,500, just like when you added them. And so this is going to be the square root of 8,500. And so maybe a bit counterintuitive. But if you think about these differences that occur, sometimes the differences are really, they can be close to each other, but sometimes the differences are a lot. You'll get a value way on the left over here and a value way on the right over there. And so a lot of times there's a really big difference, and a lot of times there's a smaller difference. But so you just have to know that. And then it says this. So we have, what's the probability she makes more pies than cakes? Think about this. So we have this new distribution here that's P minus C. New distribution here that's approximately normal, that's P minus C. It is centered at 100. Okay, and then there's its variability, there's its standard deviation. And so if she makes more from pies than cakes, so what that means is that somewhere down here is 0, where pies would equal cakes. If she makes more from pies than cakes, that would be all these points over here. It's wherever pies minus cakes is greater than 0. And so what we'll do to find this area greater than 0 is do normal CDF. Normal CDF from 0 to infinity. Our mean is 100, and our standard deviation is the square root of 8,500. And so there's our lower bound, there's our upper bound, there's our mu, there's our sigma. And in fact, when you do this, you get 0.860962. Certainly a lot more than half the time. And that sort of makes intuitive sense because you're expecting most of the time she's going to make more from pies than cakes. And that is what that answer is telling us. So that is how you handle what percent of the time is one curve more than another, is you come up with a new curve and subtract them, and then you say, well, if pies are more than cakes, that means P minus C is greater than 0. If it was cakes is more than pies, then it would be less than 0. It would be down here. So that's how you handle, in essence, the difference of two random variables. But then it says this. All right, so then it says, if you were to randomly select a week, what is the probability that Anita makes at least 50 more from cakes than pies? So there's, a couple of different ways that you could, in essence, look at that. But I'm going to say this. I'm going to say, well, it makes 50 more from cakes than pies. I'm going to say, well, what is a random variable cakes minus pies? Well, if you say cakes minus pies and subtract them in that way, it will be an approximate normal distribution. And then now cakes minus pies, so the mean is 400 minus 500. It's negative 100. But once again, the standard deviation, you have to add the variances. You have to square these two and add them. It's still going to be that, the square root of 8,500. Okay? All right. And so now our distribution is this. Here's cakes minus pies. It is centered at negative 100. Okay? And there's its standard deviation. The question is, when is cakes minus pies greater than 50? In other words, 50 is going to be somewhere down here. There's 50. What percent of the time is cakes minus pies going to be greater than 50? Like that. And so you would say, well, that's going to be normal CDF from 50 to infinity. Our mean is negative 100, and our standard deviation is the square root of 8,500. Label that lower bound, upper bound, mu, and sigma. If you don't label those, you'll just get partially correct. And so that, in fact, according to my records, is 0.051878. So it's not that likely to happen. It's on the verge of what we would call statistically significant as far as being a really unlikely event. But she is unlikely to make at least $50 more from cakes than pies. And that would make sense. I mean, in general, she doesn't make more money from cakes than pies. But anyway, now both of these problems you could have subtracted the other way and gone with sort of kind of a vice versa sort of reasoning. If you'd said cakes minus pies here, it'd be negative 100, and it would have kind of flipped the problem. So anyway, and then is this. All right. The last thing is when you randomly select 2 weeks, what is the probability that Anita makes at least $950 from cakes? So what we're doing here is she's making at least $950 from cakes. So what that means is we're in essence taking a value from random variable C, which is mean of 400, standard deviation of 70. So let me write that here. Random variable C is a normal curve, mean of 400, standard deviation of 70. So there's no pies involved here. It's just the cakes. If I take two values from that, what's the probability to be greater than 950? So we're taking one value and adding another value. We are saying random variable C plus random variable C. Okay, guess what? It will also vary approximately normally. It's going to average C, the means, you just add the means, and so that's going to be 800, but guess what? You cannot add the standard deviations. You have the variance of C is equal to 4,900. And so therefore you say the variance of C plus C is going to be 4,900 plus 4,900, and so that is equal to 9,800. So that is our new variance, and so our standard deviation is the square root of 9,800. And so then what's the probability of getting greater than 950 on that? Well, we would say normal CDF from 950 to infinity. Our mean is 800. Our standard deviation is the square root of 9,800. So that's our lower bound. That's our upper bound. That's our mu. That's our sigma. And so, and when you do that, so this would be 0.064857. So it's sort of an unlikely thing to happen to get a value to make that much money from cakes over 2 weeks, but it's sort of a plausible thing. Now, the potentially really confusing thing about this problem is there's a difference in the world of random variables between C plus C and 2C. Okay, and that's sort of an important distinction. C plus C means you're taking one value from a normal curve and then you're taking a second value from a normal curve and adding them. Whereas random variable 2C just means you're taking one value and multiplying it by 2. And so that would be different. So C plus C, if you're taking two different values and adding them, you have to add their variances. But 2 times C, well, okay, the mean's going to be the same for 2C as 800, but you can just multiply the standard deviation by 2 and get 140. So they're going to vary differently. Because if you're just taking one value and multiplying it by 2, you're in essence just getting that, there's no variability that you're getting out of that. Whereas this is going to be two different values. So in the world of random variables, C plus C is not equal to 2C. Now, and that may be a bit confusing. Let me offer this one example. This is not an extremely popular problem, but it certainly can happen. So let me offer an explanation that could help as to why in the world of random variables, x plus x is not equal to 2x. All right, let's say our random variable x is the roll of a 6-sided die. Let's just pretend it's the roll. So it is going to be, you could get a 1, 2, 3, 4, 5, or 6. And of course, the probability of each of those is 1/6. Okay? Now, random variable 2x means this. It means you're rolling a die one time and multiplying that value times 2. So if you roll a 1, 2x is going to be 2. If you roll a 2, 2x is going to be 4, and so forth. 6, 8, 10, and 12. So in each of those probabilities is 1/6. So this is 2x means you're rolling the die just one time and multiplying it times 2. So there's no way you can get an odd number. So each of those is 1/6. 1/6, 1/6. And so what now, let's say you did this. Let's say you rolled the die once and you rolled it again and got another value. That is random variable x plus x. You're getting two different values more than likely. You're rolling it twice. Well, now you could get 2, but you could get the odd numbers. You could roll a 1 and a 2 and get a 3. So 4, 5, 6, 7, you could get odd numbers. When you take a die and roll it twice and get two different numbers in essence, you could get all the numbers between 2 and 12, including the odd numbers. And as we discussed earlier in the year, what are the different probabilities here? Well, there's only one way of rolling a 2, and so there's one chance out of 36 possible different rolls that could happen. And so we created this distribution earlier in the year. The probability of rolling a 4 would be 3 out of 36, and so forth. And then all the way to 12 is 1 out of 36, and the probability of rolling 11 is 2 out of 36. The probability of rolling a 10 is 3 out of 36, because you could roll a 5 and a 5, or a 4 and a 6, or a 6 and a 4. That's 3 different rolls out of 36 possibilities. Probability of rolling 9 is 4 out of 36, and 5 out of 36. 7 is the most likely roll. And so, anyway, so 2x is very different than x plus x. This is they're going to have the same mean. I mean, their mean is still going to be, right here, the middle, which is going to be 7. So the mean is going to be 7, but their variability is different. Their variability is different because this one you're just rolling it one time and multiplying it by 2. This one has 2 different values more than likely, and you're adding them together. So that is the little tricky thing. And so when you have a normal curve, so let's not to belabor the point, but let's say if I have a bunch of apples and they have their weights follow a normal curve, mean of, 10 ounces, standard deviation of 2 ounces, let's just say. If I get, and so we'll call that random variable A, if I take one apple and multiply its weight by 2, how could that possibly vary? Well, it's multiplied by 2. So this would just be 20, and that would be 4, and I'm done. But what if I get 2 different apples and add them? A plus A. If I get 2 apples and add them, it'll also vary approximately normally. A plus A, so that would be 20. I have to add the variances. So I add the variance twice, so that would be 4 plus 4. So this would be the square root of 8. A different variability going on. Thank you for paying attention. I know those are 3 of the tougher problems that we're going to have. So I wish you all the best.